Hello everyone, today let's solve the problem 202 happy number. So let's see what the question states here. So a happy number is found by repeatedly replacing a positive integer with the sum of its squares of its digits, right? Sum of the squares of its digits. If the process eventually reaches 1, then the number is said to be happy. If it falls into the non-1 cycle, then it's not, right? So we have to return true if n is happy, otherwise if n is not happy, then we have to return false in that case, right? So let's discuss the same here. See here, we have been given n equals 19. First what we'll do, we'll square this particular number 1 and 9 differently, right? So 1 square plus 9 square will be going with, so this one is 82. So right, so 82 again will square the 8 and 2, right? So this will lead us to the this one. 8 square is 64, 64 plus 2 square 4, nothing but the 68. Again we'll square 6 and 8, right? So this one 6 square is nothing but 36 and 8 square is 64. Again it will lead to this one 100 basically, right? So 100, this one, when we square 1 0 and 0, finally it will lead to 1 plus 0 plus 0, right? So this will lead to 1. At the end it has led us to the 1 basically, right? So when it leads to 1, what we need to return, it is said to be happy and we need to return true here in this case, right? Accordingly with the question, so we'll return the true boolean value true. So let's come to the example 2 here. See here, so we'll go with n equals 2. 2 square 4, 4 square 16, again 16, 1 square plus 6 square, it will lead to this one 37. So it goes on like that, but it will never lead to the this one 1 basically, right? So in that case, this one n is said to be unhappy, and we have to return the this one boolean value false, right? So you can just check that one, n will be unhappy, and in this case we have to return the boolean value false, right? So I hope the question is clear. They have given us wonderful examples just for the sake of understanding, right? So now let's do one thing. Let's quickly discuss the approach followed by the this one complexities, and then let's write the code. Let's consider this example itself, right? So the first example, n equals 19 they have given, right? So we'll be going with a simple math here. We'll be making use of simple math, right? So the approach that we'll be going with here is simple math. Just remember this one. So let's move on with the this one further steps. The first step here would be we have to compute the next, that is equal to the sum of squares of the digits, right? So first let's consider same thing here, 1 9. So this one we will square, they have given in the explanation itself here, this one 1 square plus basically 9 square, right? So this one will lead to 82, right? So this is fine, right? So we will repeat the same basically. For the second one we'll be going with basically 8 2 we have got here, right? So this is nothing but 8 square plus 2 square, right? So this is nothing but 8 square plus 2 square, 64 plus 4, nothing but 68 here, right? 68. So this is fine. Next the third one will be going with 6 square plus this one 68, we got 6 square plus 8 square, nothing but 36 plus 64, which will lead to 100 basically. The fourth step, again they have given in the explanation itself, again I'm telling. So this one will be 1 square plus 0 square plus 0 square, so this will lead to 1. So we have got the output 1 finally, right? So when we have got the output 1, the n is said to be happy and we need to return true, right? So since we have reached 1, accordingly with the approach, so 19 is said to be the happy number here. So n equals 19 here, right? So this one is said to be the happy number. For the happy, I'll just write h here, happy number. So to detect the loops efficiently, so this is completely math based, I have said this one earlier itself. To detect the loops efficiently, we will be making use of the Floyd's cycle finding. So yesterday itself we have discussed the Floyd's algorithm as well, if you are following the algorithm playlist basically, right? And the linked list algorithm, we have discussed about the Floyd cycle detection algorithm, right? So to detect the loops, we'll be making use of Floyd's cycle finding. So this one, I'll just go with Floyd's cycle finding, right? So detect the loop, we'll be going with a Floyd's cycle finding, right? So just remember this one, man, this is important. So to detect the loop, we'll be making use of the, or we'll be going with the this one, Floyd cycle finding. So what we will do when I say Floyd cycle finding, just remember this one, will move one pointer by one transform and another one by two transforms, right? So we'll move one pointer by one transform and another by two transforms basically. If they meet at one, then it's said to be happy, right? They meet at one, then it's said to be happy. Otherwise they meet in a loop, otherwise they'll meet in a loop. So otherwise they'll meet in a loop basically, right? So then it's said to be unhappy, and then we'll return this one false. If it is 1, then what we'll do, we'll return true, right? So else they'll meet in a loop and we will return false. For false, I'll just write F here, don't get confused here, right? So this is the main this one approach basically. So this we have to implement in the form of code. See here, 1, the output that we got here is 1. So what we will return, so we'll return the boolean value true. So we have got true here, which is equivalent to the output that they have given for the example 1 within the question. So our approach works absolutely correct. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities. So what will be the time complexity here accordingly with the approach that we discussed? So the time complexity would be big O of logarithmic n. So why it is big O of logarithmic n basically? So each transform scans all the digits, nothing but big O of d, where d is nothing but d is almost equivalent to the log n to the base 10 basically I'm speaking of, right? Log n to the base 10. So Floyd needs a bounded number of transforms before cycle or 1. So overall proportional to the digits I'm speaking of here. So overall time complexity would lead to big O of logarithmic n to the base 10. So this one big O of log n I can write in simple terms. I can just go with the big O of log n time complexity. So what would be the space complexity here? Space complexity would be big O of 1. Why it is big O of 1? Because we'll be making use of only few integer variables, no extra data structure. So we'll not be making use of any extra data structures here. So we'll be going with a big O of 1 space complexity, overall space complexity. So the time complexity would be big O of logarithmic n, and the space complexity would be big O of 1 for the code that we'll be writing in the future, right? So now we are completely familiar with the complexities and the approach, right? As we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. So the first step would be here. So if it is already 1, then it's said to be happy, the base case, right? Or if n is 1 directly. If n is already 1, then it is said to be happy. So in that case, we have to return true. So this is the base case basically. This is fine. Now, as I've said, as we had discussed earlier, so we'll be going with a Floyd cycle detection algorithm, right? So we'll be going with Floyd cycle finding. So I have said this one multiple times. So when discussing the algorithms, it will be good. So if you understand the algorithm, that's fine. During the implementation, it will be fun basically. It will be fun, and if we remember the algorithm correctly, then we can implement in a good way, right? So now, yesterday itself we have discussed about the Floyd cycle detection algorithm. We have got the opportunity to implement the same thing in this particular problem, right? So just implement the same. Now let's go with the Floyd cycle detection algorithm. So slow moves 1 step and fast moves 2 steps, right? So this one, and slow equals n, and also let's go with fast equals n, right? So this is fine, man. So we are just initializing the tortoise and hare here. So this is nothing but the tortoise, and this is nothing but the hare algorithm. So hare, sorry. So one more thing I want to tell you here is, so Floyd cycle detection algorithm is also known as tortoise and hare algorithm, right? So tortoise moves slow because we are moving slow pointer once. So that is the reason we'll be considering this one as the tortoise basically. Slow pointer is considered as tortoise, and the fast pointer is considered as hare algorithm. This one hare, right? So this moves fast 2 steps, right? So this moves only 1 step. This is tortoise, slow pointer, fast is nothing but the hare here. This is fine. Now let's do one thing. We have initialized tortoise and hare. So let's go with the do while loop here. So we haven't or I haven't used do while loop in this one while basically. Let's make use of it. So let's move slow by 1 transform, nothing but the slow pointer I'm speaking of. So this one will be slow I'll be making use of the sum of squares, this one, what do we call, helper method here. So to let's go with the helper method sum of squares. Let's write that one and let's make use of it within the main method. So I'll just go with private int, so I'll just go with sum of squares here, right? So I need the parameter x, which is of the type int. This is fine. So within the sum of squares method, so we have to go with the accumulator for the sum, right? First I'll just initialize the s to 0. This is fine. Also let me make use of the while loop. So this one, while x is greater than 0, then let's extract the last digit. So this one will be int d equals x modulo 10. This is fine. We are just extracting the last digit. After extracting the last digit, we have to add the square of the digit, right? So I'll just go with the s equals s plus d square, nothing but d into d here. This is fine, man. Finally, we have to drop the last digit. So this will be x equals x by 10, right? So I can just write it on this way, x equals x by 10. So we have to return the computed sum or the calculated sum. For that, nothing but we have to return s in simple terms. I'll just go with return s. So this is it for the sum of squares helper method, right? So I'll just make use of the same helper method within the main method now. So we are making use of the do while loop here, right? So we are moving slow by one transform, nothing but the slow pointer I'm speaking of. So let me make use of the helper method sum of squares here. Let me pass slow, and also for the fast we'll be going with the 2 steps, right? So again, sum of squares, this one, this one, this one, right? 2 steps, right, at a time. So again I'll just pass here within the sum of squares, I'll pass sum of squares of, so let me go with a fast, right? So this is fine, man. Finally, we have to make use of the while loop here. So we have to loop until they meet, right? So to detect the cycle, if it is unhappy, we have to return false in that case, right? So while slow not equal to fast, so this is fine, man. Yep, while slow not equals to fast. So finally what we need to do, we are done, we are left with only one step. If meeting point is 1, then the number, or then n is said to be happy. Otherwise it is trapped in a cycle, right? It is trapped in a cycle. Then it is said to be not happy or the unhappy, right? So let's return true if it is happy. So we have to check whether this one slow is equivalent to 1 or not. So this is it for the code. So let me format the code once and let me hit the run button. So this has to work. Let's see. So yeah, you can clearly see here the sample test cases are getting passed. So let me hit the submit button quickly. So here you can clearly see all the test cases are getting passed. So whatever the code that we have written works absolutely correct. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.